These are the answers to homework 5B. Here are the definitions I would like you to know. And now on to the questions. Number 1, calculate the moles of gas contained in a 986 milliliter flask at 29.2 degrees Celsius with a pressure of 688 torr. So when you're asked to solve for one particular variable of a gas, you can use the ideal gas law equation PV equals nRT. In this case, we're trying to solve for the number of moles of gas, so I'm going to isolate N, and the number of moles is going to equal the pressure times the volume over R times T. To use the universal gas constant of R, 0.08206 liter atmospheres per mole Kelvin, P, V, and T have to be in the particular units of atmospheres, liters, and Kelvin. So in this particular problem, the pressure was given as 688 torr. That's not the proper unit, so you'd have to convert the torr into atmospheres by the equality statement 1 atmosphere equals 760.0 torr. Here the torr cancels out, and the pressure we're going to use in the equation to 3 significant figures is 0.905 with a guard digit of 3. The volume was 986 milliliters. The conversion to liters can be done in your head, 0.986 liters. And the temperature, 29.2 degrees Celsius, can be switched to Kelvin by adding 273.2. So once all the numbers have been plugged into the equation with their proper units, it's 0.9053 atmospheres multiplied by 0.986 liters, divided by the universal gas constant, and divided by 302.4 Kelvin. Atmospheres cancel out, liters cancel out, and Kelvin cancel out, and the answer will come out in moles and to 3 significant figures. This container must have 0.0360 moles of gas. Number 2, calculate the density of ammonia gas at 27 degrees Celsius and 635 torr. When you're trying to solve for the density of a gas, I would use the alternate form of the ideal gas law equation, PV equals mass over molar mass, RT. And the density is mass divided by volume. So in this equation, it's not the molar mass, it's the mass. It's M divided by V. So the V is moved down to the bottom under the M, and then the molar mass is moved to the top on the left, and the RT is moved to the bottom on the left, and you will have isolated this equation for M over V. Why do we do that? Because M over V is density. So the density is going to equal the pressure multiplied by the molar mass divided by R and T. The pressure has to be converted into atmospheres. And so if you do that, you come up with 0.835 with a guard digit 5 atmospheres. The molar mass of ammonia, you add up the molar masses of 1 nitrogen and 3 hydrogens, it's 17.04 grams per mole. The universal gas constant, 0.08206 liter atmospheres per mole Kelvin. And when the temperature was switched into Kelvin, because it was 27 degrees, it was only accurate to the ones place. When you add 273.2, your answer is going to have to be rounded to the ones place, so it's actually just 300, and then the 0.2 is a guard digit. This will wind up giving you an answer that's 3 significant figures. The final units that work out are grams per liter, and I get the density of the ammonia gas to be 0.578 grams per liter. Problem number 3. A compound is found to be 24.8% carbon, 2.1% hydrogen, and 73.1% chlorine by mass, period. When the compound was vaporized, a 256 milliliter flask at 373 Kelvin and 751 torr contained 0.800 grams of the gaseous compound. For the compound, determine 3 things. A, its empirical formula. Well, the empirical formula can be determined from the percentages given in the problem. If we know the percent by mass of carbon, hydrogen, and chlorine, we can assume we have 100 grams of the compound, and so 100 grams of the compound would therefore contain 24.8 grams of carbon, 2.1 grams of hydrogen, and 73.1 grams of chlorine. To determine empirical formula, the ratio of 24 to 2 to 73 has no meaning whatsoever. We have to convert the mass of each of these into moles. And when you do an empirical formula determination, you're trying to figure out how many atoms there are of each element in the compound. So we're going to use the molar mass of atoms. So the molar mass of carbon atoms would be 12.01 grams per mole. And this is why I specifically said that. You're not trying to find how many diatomic molecules of hydrogen are in the compound. You're trying to find out how many hydrogen atoms. So I would use the molar mass of atomic hydrogen, which is 1.01 grams per mole. And the same thing for chlorine. You're not trying to find, when you do an empirical formula determination, how many diatomic chlorine molecules there are. You want to know how many chlorine atoms. So whenever you do empirical formula determinations, use the molar masses of monoatomic substances. If you're doing a chemical reaction and chlorine gas is reacting with hydrogen gas, those are diatomic. You would have to switch grams to moles or moles to grams with the diatomic molar masses. But in this case, I get these three number of moles of carbon, hydrogen, and chlorine. And once you've done that, you divide them all by the smallest number, which is 2.062. When I do that, I get a 1:1:1 ratio, which means my empirical formula is CHCl. That's part A. Part B says, what's the molar mass of the compound? It doesn't mean to add up 1 carbon, 1 hydrogen, and 1 chlorine, because that may not be the real formula. That's only the empirical formula. The molar mass is going to come from experimental data, and it's all the other data in the problem. They said they took the compound, they vaporized it. It was in a 256 milliliter flask. Its temperature was 373. Its pressure was 751. And then it weighed 0.800 grams. There's enough data in there to use the alternate form of the ideal gas law equation. You can plug in pressure, volume, mass, and temperature, and you can solve for the molar mass. So this is what you needed to do in problem B. So to solve for the molar mass, we're going to take the mass of the gas, multiplied by R, multiplied by its temperature, divided by P, and divided by V. So the mass of the gas was 0.800 grams. The universal gas constant's given. The temperature was 373 Kelvin. The pressure had to be switched to atmospheres, so that turned out to be 0.9882 atmospheres. And the volume switched to liters was 0.256. And all the units cancel out except for grams per mole. And so this allowed us to calculate the molar mass of the gas, which should have been 96.8 grams per mole. This is a typical technique for using the alternate form of the ideal gas law equation to calculate the molar mass of a substance. Quite often, the substance isn't a gas at room temperature. So what they did is they heated it up to 100 degrees Celsius. They took a flask of the liquid material, let's say it's a liquid, and you put the flask in boiling water. The contents of the flask therefore reached 100 degrees, and if the substance were to vaporize, you would then collect a gaseous form of the unknown in that vapor that's sitting in the flask in the boiling water. So while it's at 100 degrees Celsius, you determine the pressure and the temperature. Then you take the flask out of the boiling water and you let it cool down, and the vapor will condense into a little drop of liquid, and then you weigh that little drop of liquid. That was the mass of the substance when it was a gas, but now it's condensed to a liquid, and you get its mass of 0.800 grams. That's how the mass of a gas is determined. So you're able to determine mass, temperature, pressure, and volume, and we can get the molar mass to be 96.8 grams per mole. Now we can do part C. What's the molecular formula of the unknown? Well, if we know its empirical formula is CHCl, what you do is you calculate the molar mass of the empirical formula. This came out 48.47 grams or 48.47 grams per mole. Then we take the molar mass we calculated the substance really has to have, which is 96.8, and we go the molar mass of the real compound divided by the molar mass of the empirical formula, and that'll be really close to an integer. In this case, it comes out almost exactly 2, and so that means the real molecule must be twice as big as the empirical formula, so therefore C2H2Cl2. Question 4, I want you to draw a qualitative graph, which means you don't have to put numbers on there, just sketch what it would look like, to show how the first property varies with the second property in each of the following. In each case, assume that moles are constant. So in 4a, they ask for the graph of pressure versus temperature. To figure out what the relationship is between pressure and temperature, I would take the ideal gas law equation, and I would hold every other variable constant. So V and N and R all have to be constants. And so if I combine all the constants to 1, I get P equals K times T. This should tell you the answer to the question, because the P and the T are on opposite sides of the equal sign, both in the numerator. That means they're directly related. And whenever you graph a direct relationship, that graph is going to be a straight line. So this is what your graph should have looked like. Notice I'm crossing it at the origin. That's because the intercept would be 0. If T is 0, P has to be 0. So you can absolutely say that the line must cross at the origin. That's A. B says, let's graph pressure versus volume. So if you want a graph of pressure versus volume, once again, I would go to the ideal gas law equation. I would make the moles and the temperature constant and only keep the P and the V as the variables because they're the only things we want to see what they're related to each other. Combine all those K's into one, and I have this relationship here. This should tell you the answer. If the two variables you're graphing are on the same side of the equal sign multiplied by each other, they must be inversely related, and you need to know what an inverse relationship looks like. It graphs as a hyperbola, and so this graph should have looked like this. C, graph P versus 1 over V. So if we know that we want to graph P versus 1 over V, and we have our ideal gas law equation, the only variables in here we want to graph are pressure and volume. So just like the last one, I'm going to assume that everything else is a constant, combine them into one constant, but I don't see a 1 over V in this equation, so I'm going to have to make a 1 over V. So I'm going to divide both sides of the equation by V, and then when I do that, I'm going to take the right side, I'm going to break it apart into two factors. I'm going to go K multiplied by 1 over V, because it's the same thing. Now I have a pressure and a 1 over V in my equation, so now I can make my graph. And because the P is on the left side and the 1 over V is on the right side, they're on opposite sides of the equation, that means you're going to get a straight line graph. The graph would have to look like this. D, graph log of P versus log of V. So now if we're going to graph logs, I'm going to start with my second highest or second lowest equation here, and I'm just not going to derive all the stuff this time, but I'm going to start right here with P equals K over V. But I could actually start with PV equals nRT, derive PV equals K, and then get P equals K over V. But just to save a moment, I'm going to start with that. So if you want to graph log of P versus log of V and predict what the graph will look like, I would take the logarithm of both sides of this equation. So the log of P would equal the log of K over V. And on the right side, because of the rule of logs, that can be simplified to be log of K minus log of V. And if I take the two terms on the right side of the equation and reverse them, I put the negative log of V first and the positive log of K second. The reason I do this is this fits in the form Y equals MX plus B. This has to be a linear relationship. So if I graph log of P versus log of V, it's going to make a line. In this case, the slope is that -1 that's in front of the log of V. So the slope is going to be going down, and the intercept is not going to be at the origin. The intercept's going to be at wherever the log of K is. So you're actually going to cross the y-axis at some point, but that point would be log of K. But nonetheless, it would turn out to be a linear graph. Final one, E, graph PV versus V. So if you're ever graphing a product of variables on one of the two axes, you got to try to figure out what is that product of variables. What does P times V equal? So I once again start at this point, P equals K over V. Let me multiply P times V together and see what it makes. It makes K. That means it's always a constant. So if I were going to graph PV on the y-axis, the numerical value of P times V is always going to equal K, and the only way it can always be the same number is if the graph turns out to be a horizontal line.